So today we will discuss about especially quadratic program, and if only quadratic program is mentioned there, that means by default constant would be linear in nature and objective function would be quadratic in nature, and there would be one more generalization of quadratic program that we are calling it quadratically constant quadratic program. That means objective is quadratic as well as the constant involved happens to be quadratic in nature. Then, so those kind of problem we will discuss, and we will try to, from the solution perspective, we will try to solve only convex quadratic program. And how to solve all those things I will discuss in detail. And also I will take few problem from different courses so that those problem can be converted into convex quadratic problem. Yeah. Initially, it would be not a mm, convex problem; it would be a quadratic problem. But after applying some kind of transformation, we can convert that problem into a convex quadratic problem. And once it is in convex quadratic problem, then easily we can solve with the help of CVX. So outline of today's lectures are the following. First, I would like to discuss about quadratic program. I will give detailed analysis of quadratic program and what is the general form, and a few example also I will discuss. In between, we had already seen several quadratic program, but I will recall those example as well. And I will take few specific example. Those will directly come from some kind of data analytics. And uh, in the last module of this lecture, I will talk about QCQP, that means quadratically constant quadratic program. And I will give you example of this kind of problem as well. So coming to quadratic program, where we are putting convex criteria, that means our objective function must be convex in nature. So it is totally dependent on the coefficient function involved in the quadratic form. So first, I am talking about problem formulation of convex quadratic program. So a quadratic program in the convex form, it can be formulated as that we have to minimize a quadratic function. Here we can observe that a general quadratic function can be written as uh, x transpose px plus q transpose x plus r. Here, if you we are not mentioning anything about p. If p is any general kind of matrix, then n by n matrix, then this problem would be just a quadratic problem. But when we take a condition over this coefficient matrix p, and we say that this matrix coefficient matrix p is a positive semi-definite matrix, in that case we know that from second order characterization we can easily see that this objective function would be a convex function. Why? Because if you are finding the Hessian of this quadratic function, what would be Hessian? Hessian, it would be just equal to this coefficient matrix P, and we are here already taken a condition that P happens to be a positive semi-definite matrix. That's way the objective function is a convex function. Now coming to constant, we are putting a polyhedral constant. That means matrix G time X less than component wise less than H. So it is what it is directly giving a polyhedral. Again, polyhedral happens to be a convex set. That means our feasible set is a convex set, and also we are taking uh, equality constant as an affine constant. So both here equality constant, it happens to be polyhedral, and that means a convex set. Also equality constant giving convex set. So in total, we can say that our feasible set is here. Call it C. Feasible set is also a convex set. So we are minimizing a convex function, this quadratic function over a convex set. So overall, it is a convex optimization problem. So if you want to visualize the first order optimality condition of this convex optimization problem, then easily we can visualize that if you are taking just linear constant, you can observe that here all the constant involves are either linear or affine. That means affine and linear, there is no much difference. So both are very much equivalent. So if you are taking a affine structure, then the corresponding feasible set, it would have uh, linear boundary only. So what will happen if you are trying to find optimal value of this quadratic problem, then where the optimal value will occur it will occur at the boundary point. And what happens in linear program, we had already seen that the optimal points that occurs at extreme point, but it is not true for the case of convex quadratic program. Why? Because here if you draw this one is a quadratic objective function or quadratic function, and if you draw corresponding contour line, then what is it? These are curve. These are curve in nature, so it will just touch anywhere, not only at extreme point, it may also touch on the boundary as well. So you can look into here. So here this contour or level curve, it is touching, or it is or simply also you can say that it is supporting the visible set at this point x star. That's where this x star is a optimal point of this problem. So this one is the geometrical visualization of optimality condition of convex quadratic program. So coming to example, one simplest example here I have taken linear regression. So linear regression here, if you ask me what is the constant, so it is one kind of unconstant problem. If you are not putting any unconstant problem, so I am taking a simple least square regression. So it is formulated as just we are minimizing a square of norm ax minus b. That means we are having this equation, linear equation b equal to ax. Generally it happens to be inconsistent uh, linear system. Then we try to, if it is inconsistent, then we try to find an approximate solution of this one. From linear algebra also you can get list approximate solution directly, but here it is part of convex optimization problem, so that's why we will apply the technique from optimization. So this objective function further you can express as in this quadratic form. Here what kind of function we observe here? So it is a quadratic function with coefficient function. What is coefficient function? A transpose A. Now, here A is any kind of matrix, whether you can call it design matrix or you can call it observation matrix, whatever matrix. So, but if you define with respect to this A, you are defining a new matrix A transpose A, and what is happening? So, this matrix is always a positive definite matrix. Due to that, if you talk about convexity of this objective function, here there is no constant. It is just we are having unconstant problem, and this corresponding objective function is a convex function. So easily this problem will have a uh, optimal solution. And what would be optimality condition? Just find the gradient of this objective function and equate to 0, because this problem is a unconstant problem, so that's why equate to 0. That will give your optimal point. So you have to solve this linear equation. So this kind of problem, it arises in many fields and has many names. Some book they are calling it regression analysis. Some book they are calling, if you are in linear algebra, then mostly you will see in name least square approximations. And this problem is simple enough to have well-known analytical solution. So analytical solution, it will be written as x equal to a dagger b. A dagger we call it pseudo inverse. So there are various way of representing this pseudo inverse, and also it is completely dependent on the this design matrix A. Suppose your matrix A happens to be in such a way that kernel of this matrix is a singleton set 0, then due to that it will imply that the corresponding matrix A transpose A happens to be invertible. If kernel of A happens to be a singleton set, then it implies that A transpose A is invertible. So in that case, what will happen? So this given a linear system, it is inconsistent. So what you do, this inconsistent system you can convert into a normal equation that would be solvable. So A transpose is invertible here. So if you multiply both sides with A transpose to this equation, so if you multiply with A transpose, what kind of form it will take? It becomes terms, for simplicity, I am writing right hand term in left hand side. So I am multiplying A transpose both sides. So A transpose times AX, it would be equal to A transpose B. So what is happening here? In this case, what does it becomes? So in this here it is inconsistent. So what is the criteria of inconsistent? It is simply saying that a system B equal to X is inconsistent. That means it is having no solution. When it is inconsistent, it is saying that when the right hand side given vector B is not in the column space of the coefficient matrix A. This is the criteria of being inconsistent. Now, when we multiply both sides with A transpose, then what will happen due to the property of subspaces, four fundamental subspaces of linear algebra, four fundamental subspaces of matrix? This new vector A transpose B, it happens to be in the column space of A transpose A. That means it is a solvable. This normal equation is a solvable equation, that or you can say that it is a consistent equation. So what is solution of this? Solution, easily you can say it. That means here you have take a condition that there are many other conditions. Take one condition that kernel of the given coefficient matrix is uh, having only one element 0. That means singleton set. It means that A transpose A is invertible. So due to that invertibility condition, you will get your approximate solution. Call it X star. So approximate solution would be what? So here it is invertible, and you know that matrix multiplication is associative. So you can play with here this bracket, and through that you will get here A transpose A, take in whole inverse times A transpose B. This one is the analytical solution of this simple inconsistent system. And here you can call this complete term, that means this complete term you can call it pseudo inverse. Actually A is not invertible because A is not a square, in general a square matrix. It is a rectangular kind of matrix. So we can't talk about invertibility. And also A might be, simply you can say that A is a singular matrix. Singular means either a determinant of that matrix is 0 if it is a square matrix, and otherwise it is a rectangular matrix. So if it is a rectangular matrix, there is no concept of determinant. So this total term, all these terms in total, we call it pseudo inverse, or we denote it by dagger, A dagger. So there are various concept to the way to find this pseudo inverse. One, if you are in last year, we had already discussed a lot about finding pseudo inverse using SVD. So those concepts you can apply it here in order to find pseudo inverse. Okay, so you got the solution of this given regression problem directly. This analytical solution, you got it. Now further, this one was the constant problem, unconstant problem. Further, if you are willing, you can further put any box kind of constant or whatever constant, you can put it over the given regression problem. It depends upon what kind of problem you are taking it. Problem will suggest what kind of some kind of special kind of constant here. Now I will take another example that we are calling it linear classification. I won't go in detail. I will just talk about formulation version of this one, and how to convert. If you just try to formulate linear classification problem, then it will come as a non-convex problem, but you have to apply some kind of transformation. Then it will be converted into convex quadratic problem, and once it is in convex quadratic, easily you can solve it. So what is all about this? This problem is talking about, suppose we are having two different type of points in any Euclidean space Rn. Suppose those two type we are calling it type A and type B. And the type A points we classify it to x1, x2 up to xm. M number of points are, first m number of points are type A, and last p number of points, that means m plus 1 up to m plus p, those are of type B. So we have to classify these two kind of points. So for example, suppose we are taking a few points in R2. So type A points that we denote it by asterisk, and type B points we denote it by diamond in the given graph. So these are type A point, and these are type B points. So our job is here, our objective is here, how to classify or how to separate, better if you call in term of optimization, how to separate these two class of points using a hyperplane. So how you can, so there would be definitely infinitely many. If suppose one condition we are putting it here, these two data sets are happens to be separable, so we can define infinitely many separation line. Recall the separation theorem that we had already discussed. So simply make a convex hull of these two class of points. So that means you are having two convex set, and those convex set again happens to be what, very nice structure. It is closed, also it is compact in nature. So separation theorem always guarantee there exists a separating hyperplane. So there are infinitely many separating hyperplane. So we have to find the best separating hyperplane. So how we can find that best separating hyperplane? So it will depends upon that formulation. It will totally depends upon formulation. So here, what is our objective? We have to find the best linear separator or separating hyperplane HW beta, that we didn't define this hyperplane like this way, x such that you know the definition, dot product of W with x equal to beta, which separate the type A point and type B points in both happens to be in opposite side. That means so type A points are in the strictly lower half space, and type B points are strictly in upper half spaces. If these two are mutually disjoint and happens to that corresponding convex hull are mutually disjoint and uh, compact. Definitely convex hull for finite number of points always happens to be a compact set and closed set. Compact, that means closed and bounded set in Euclidean space. So easily you can talk about existing of separating hyperplane. So coming further, assume we are putting assumption that two class of points are linearly separable. Then the problem is not well defined in the sense that there are many uh, separating hyperplane or linear separators. So what we do then? What we seek is in fact a separator or separating hyperplane that is in sense farthest as possible from all the points. So there is a need to define the notion of margin of the separating hyperplane. So that margin it will define as the distance of the separator from or separating hyperplane from the closest point. So I will go a step wise in order to define all those concepts. So the separation problem will thus consist of finding the optimal separator, or simply you can say that separator with largest margin. So here what we will do in a step one, we will define distance of any given point with respect to this hyperplane HW beta. So distance is defined by this way. It is again, if you go like this way, distance is defined by infimum in the form of so you can talk about infimum of all the distance between y and take any point from hyperplane, call it x, such that x is coming from hyperplane h. In short, I'm writing notation h. Otherwise, h is already specified by corresponding weight vector w, or you can call it normal vector w, and bias beta. So this is the definition of distance of a point with respect to a set. And if you simplify, then distance of y with respect to the given hyperplane h, it will be this ratio. That means difference of norm of w with x minus beta divided by norm of weight vector. Now in a step 2, we will define the concept of margin with respect to hyperplane. So margin, so what you do, same, that means find the all the distance of every point with respect to the hyperplane. And what we do, we will try to among those distance we will try to find the minimum one. So this we are calling it margin. Now in next our actual problem will come. That problem under consideration would be what? That means we have to maximize this margin with respect to this weight vector W, subject to constraint. That means first M, that type A points are in lower half space, type B points are in upper half space. So here you can observe that this problem is not a convex problem. Why? There is no issue with constant. Constant are happens to be convex in nature, but if you come in to see objective function, it is not convex in nature. So what we do? We have to do little bit modification. So the above problem has a degree of freedom in the sense that if suppose we are having an optimal solution, that means optimal solution, it would be in term of optimal weight or optimal normal vector and optimal normal vector of the hyperplane and the optimal bias. So is an optimal solution, and if you do any scaling of that, then again remains a optimal solution for any non-zero alpha. So a scaling is not creating any issue. So due to that, we what we do in the objective segment, we had this function. So this function we will put it into a constant part. That means taking this value equal to 1, and then the above problem will be formulated as like this way. So here I have, you can see the plot of the, you can visualize easily what is the margin. This is the margin. So what problem we are having now? New problem is we have to maximize 1 by norm of W subject to this equality constant is coming. But remember that it is not a affine condition. It is not a affine constant. Here modulus is coming. So definitely it is a nonlinear kind of things is coming here. So due to that, non-convexity pattern is coming. Subject to further constant. These are already all constants that type A point must be in the lower half space and type B point must be in the upper half space. So further what we do, the combination of the first equality and other inequalities implies that a valid reformulation it will take of this form. That means we have to maximize uh, here uh, here we had a function in the last problem. We had to maximize reciprocal of uh, norm, and this problem is equivalent to minimizing norm. And you know that whether you are going to minimize norm or whether you are going to minimize a square of norm, there is no much issue. Both will give same optimal point. Just there will be change in optimal value, but optimal point would be same. So that's way. So minimizing norm of W is equal to minimizing norm of square of W. So here it becomes now minimization problem. So we need to minimize a square of norm of W subject to this non-convex constant, and the remaining two we are defining now in new way, that W transpose xi plus beta is less than equal to -1 and W transpose xi plus beta greater than equal to 1 for these i's, and for so it is for type A kind of points, and these constants are coming with respect to type B kind of points. So again this problem is not a convex problem, it is a non-convex due to this. Here our objective function is convex, there is no issue. This one is also convex, this one is also convex, but this constant, this equality constant is not a convex constant. That means it is not a affine constant. So further we have to, what we do, just for the sake of simplicity, we will remove this equality constant, or we can call it, it is some kind of relaxation. When we are removing, then resultant problem we are getting it that we have to minimize square of norm of W subject to these two equality constant, or it happens to be uh, convex in nature. Okay, so now this problem is a convex problem. It is just fitting in the category of convex quadratic problem. So that's why I told that linear classification problem, it is actually in actual formulation, it is not a convex quadratic problem, but we can reformulate this problem into a convex quadratic problem. This one is the second example of our convex quadratic problem. Now I will talk about third example, that we are taking a linear program. Remember that we are taking here linear program with random cost. So due to this presence of random cost, it becomes a, any question? Anyone willing to ask? No question. Okay. Okay, there is issue with audio. Okay. Are you are you able to listen me now? Okay. In between, if you face any problem, then let me know. Okay, fine. I'm going forward. Now, slide is visible. Okay. So now we are taking a linear program, but remember that our cost is random in nature. So due to this random nature, this problem will be posed as a convex quadratic problem. So a linear program with random cost can be posed as a convex quadratic problem. How? It follows like this way. So we are having a linear program where we minimize C transpose X. It is a linear function, and where C is a random cost. That's way, if it is a random cost, then it can be converted into in this form. C transpose X, it can be converted as expectation of C transpose X plus uh, gamma time variance of C transpose X, subject to linear constant. These are the linear constant. Okay, so what you observe that here, if C is deterministic, then it is a linear program. But if C is not deterministic, then the objective function, it will be translated into in this form. That means here, what variance of C transpose X, it happens to be a quantity in nature. So that's way this problem becomes a quadratic problem. So that transformation I will talk it here. So where the cost function or cost factor, simply you can call it C, it is a random in nature with expectations C bar and covariance sigma, covariance matrix sigma. So variance of C transpose X, what it would be? It would be X transpose X. So what kind of form it is taking? It is a quadratic form. And remember that variance is what kind of matrix? It is a positive semi-definite matrix. Positive semi-definite, that means Sn plus. You can denote it by Sn plus. So due to that, this quadratic form, what it would be? It would be convex in nature. So in general, there is a trade-off between small expected cost and a small cost variance. So one way to take variance into account is to minimize a linear combination of expected value and the variance of the cost. That means that's where we are not only minimizing the variance, we along with that we minimize this augmented form, or this augmented form, that means augmentation of expected value and the corresponding variance. And this it is having a name. That name we are calling it risk sensitive cost. So in place of minimizing C transpose X, we are minimizing risk sensitive cost. So we had already seen enough example for convex quadratic problem. Now second kind of problem in quadratic form, it will come as quadratically constant quadratic program. So what is that? So it is talking about that it is a problem consisting of minimizing a quadratic function subject to quadratic inequality, and inequality is constant. Okay, so this kind of the general form of a QCQP, you can say that like this way. You're here, you can observe that your objective function is what quadratic in nature, and here remember that your coefficient matrix P naught. P naught is positive semi-definite. Why? To make this one convex. So why? Again, I will talk about Hessian of this objective function. What would be Hessian? Hessian would be P naught, and P naught is a positive semi-definite matrix. That's way from second order characterization you can say that your objective is a convex function. Now coming to inequality constant, again this inequality constant you are having m number of inequality constant, and here each coefficient matrix Pi happens to be positive semi-definite matrix. It is given here. So due to that, these inequality constant are again convex in nature. Convex in it is giving a convex feasible set. Similarly, equality constant Ax equal to B, it is also giving a convex structure. So in total, you are having a convex objective function over convex feasible set. So this one is a convex program. So one example I would like to take in this case, what is happening. So if you are taking a special class of function that in general function happens to be non-convex, but what you do, take in that non-convex problem, you can define a small class of uh, sub-problems. Those sub-problems in a trust region, it can be converted into a convex problem. So that means in those kind of problem convexity is hidden there. So hidden convexity in trust region problem is appearing there. Trust region is just talking about a small neighborhood of problem in a small neighborhood, localization of the given problem. So there are several situations in which a certain problem is not convex, but nonetheless can be recast as a convex optimization problem. This situation we are calling it hidden convexity. In the last case, in linear classification, we had already seen that. Perhaps the most famous non-convex problem possessing such kind of property that hidden, that means hidden convexity property is, we are calling it trust region subproblem. So it is consisting of minimizing a quadratic function. It may not be a convex function. This quadratic function may not be convex, subject to Euclidean norm constant. That means we are minimizing a function x transpose ax plus 2 times b transpose x plus c. That means this quadratic function subject over that x is coming from a unit ball. Here, remember that here A is a just symmetric matrix. So due to symmetry, we can't say that this quadratic function is a convex function. Why? Because Hessian would be just a symmetric matrix. To pick constant symmetric matrix A. Hessian is A, and A, we don't know whether this A is positive definite or semi-definite. So that's where the objective is not a objective function is not a convex function. So what we do here now, one idea we are having A is a symmetric matrix. Then there is a very famous theorem from linear algebra that we are calling it a spectral theorem. From the spectral theorem, you can decompose the matrix, symmetric matrix into three matrices. Here, matrix U times D times U transpose. Here, U is what? U is orthogonal matrix. And we know that if U is orthogonal matrix and you do transformation of that, then again that remains a orthogonal matrix. So orthogonal matrix is invariant with respect to transpose, orthogonal matrix. And D is what? Diagonal matrix, where diagonal elements are coming from the eigenvalue of A. So this one, this result we are calling it a spectral result. So it is only true for the case of symmetric matrix. If it is not symmetric, that means A is in rectangular in size, then that time you have to do SVD. Parallel theory is directly coming from SVD. So you can apply SVD in order to convert the trust region problem into a convex problem. So here, when you apply this spectral theorem, then the above problem, it will take up the form, uh, because here you are writing A equal to U times D times U transpose. So the corresponding optimization problem will take this form. Okay, and remember that here what is U is a upper it is a orthogonal matrix. So what is the inverse of U? Just do transpose. That U transpose would be inverse of U. That means if you multiply U with U transpose, you will get identity matrix. Okay. So here there is no issue with here. We had already X transpose in the objective function. We had X transpose A X. So A has been factored into these three matrix, a special kind of matrix. So that's why we have written in place of A, we have written U D U transpose. That means this quadratic form is taking X transpose U D U transpose X. Now coming to this linear factor. In linear factor, in the objective function we had just twice of B transpose X. Then how U into U transpose is coming? I mentioned that here U into U transpose happens to be anti-matrix. That's why this term is coming here. Now, again, one more property of orthogonal matrix is that if you multiply any vector with orthogonal matrix, then it is uh, non norm invariant, or you can say that length invariant. That means norm of ux it would be equal to x. It is a very interesting property of orthogonal matrix or orthogonal transformation is that orthogonal transformation is it is not invariant with respect to angle and with respect to norm. That means if you are taking any two vector and you apply orthogonal transformation or orthogonal matrix, it is not going to alter the angle. Also, it is not going to alter the angle between those two vectors. Also, it is not going to alter the length of the vector. So that's where these two properties are inherited in the orthogonal matrix. So that's where here, in place of uh, this criteria I have taken, U is orthogonal, so U transpose is also orthogonal. So norm of U transpose X equal to norm of X. So I have substituted, just replace this norm of X by norm of U transpose X. So this condition is coming. So the last problem has been posed like this way. Now again, this problem is not a convex problem. Why? Because of this D. D may have the here D contains eigenvalue of diagonal element of D has are coming as eigenvalue of A. So definitely A may have non-zero non-negative eigenvalue as well. Non-positive eigenvalue as well. That means some negative eigenvalue as well. So making this linear change of we do linear change at y equal to u transpose x, then it will take very simple form that we need to minimize y transpose dy plus 2b transpose uy plus c, where y is coming from this unit wall. Okay, so this problem is again it is not a convex problem. So what we have to do? So we have to apply the concept of sign of optimal decision variable in prior, and due to that, it will be converted into a convex quadratic problem. Okay, it is already 45 minutes. So if you are having any doubt, you can ask. Otherwise, other things we will cover in next class, and uh, probably next class onward we will start duality.